Hi everyone, I'm Rohit Kumar Singh, the TA for this course, Nuclear and Particle Physics. And today we have the extra session for this course, and this will be the last session. So, so in the last week, we discussed the weak interaction and how we cannot have mass terms in the Lagrangian explicitly because it leads to various problems. So then the I just briefly mentioned that the way out is called something called spontaneous symmetry breaking, and so I wanted to. I didn't discuss that last time. We solved some examples and then we concluded the session. So I wanted to discuss that in this session. What is spontaneous symmetry breaking and what does it mean? So I'll try to briefly, discuss it. So as I mentioned, the problem uh, with the weak Lagrangian uh, that we saw last time. So if uh, if we explicitly introduce uh, a mass term like you know something like sorry. So experimentally, it was found that the weak bosons are massive, right? So we should have a mass term like this inside the Lagrangian. So something like this. But and then there are other parts of the Lagrangian. But the problem is that when we uh, do the gauge transformation of this term, we see that it's not invariant. That is, we get something extra when we have the gauge transformation of this term plus something which is non-zero. And so uh, so we cannot have such a term inside the Lagrangian, right? Because Lagrangian needs to be gauge invariant, and having non-gauge invariant terms. So yeah, so you may ask, what is the problem? Can't we have a term without, which does not have gauge invariance? So what problem does it lead? So it leads to various problems while calculating quantities like cross section, which are of interest when we are studying these systems. So that's why we cannot have a non-gauge invariant term. And we said that we cannot break the symmetry explicitly. Okay, so cannot break the symmetry explicitly. Symmetry means so when we do the gauge transformation, it should be invariant. So that is the symmetry that we want, and it breaks when we add terms like this inside the Lagrangian. Uh, Okay, so the way out was a formalism called spontaneous symmetry breaking. Okay, and uh, spontaneous symmetry breaking. Now, what does it mean? I mean, uh, so, I mean, let me first give you a naive example. So, suppose you have a circle or a sphere like this, okay? And if you rotate it, uh, it is invariant. I mean, if you rotate it, it still looks the same, right? So, invariant under rotation. But if you introduce some deformities in it, so like this, and now you rotate it, uh, it looks different, right? So this is how you explicitly, by introducing something in the system, explicitly breaks the symmetry, which is the rotation symmetry here. Now, what a spontaneous symmetry breaking means is, so suppose there is a, you know, you went to a hill station, there is a hill like this, okay? It is perfectly symmetrical around this point, and you are standing here, so you are standing here, okay? And you see that it is perfectly symmetrical around I mean, reflect, you have a reflection symmetry, right? If you are at point A, but if you move to a point B, okay, uh, you don't see the symmetry anymore. You see that there is a hill on your left which is higher, and then there is a hill on your right which is lower. So this is but the system doesn't change. The hills, I mean, the landscape is same, but it's your point of view that has changed, which has broken the symmetry that you were seeing. So this is kind of what it means, that spontaneous symmetry breaking, okay, at point B. Now, uh, to understand this in the formalism that we are going through, so uh, we will do this through a toy model, okay? The formalism about how the spontaneous symmetry breaking works, and then I will give you a analogy, I mean a simplified analogy, so that you will understand it, okay? And okay, so the toy model that I want to that we can take is something like this. So toy model, so we consider a Lagrangian which has a term like we had in the like we had the in the electromagnetic theory. So this is for the vector field. Okay, and then we have a scalar field term. Okay, and we know that so also this vector field strength tensor, you might say, it is given similar to what we had for the electromagnetic case. Okay, and it has the gauge invariant transformations given like this. Okay, where lambda is parameter, and phi uh, it transforms like this. Okay, so this is the scalar field phi, and we can write the Lagrangian for the scalar part. If you remember, we use du instead of delta u, del u, to have the gauge invariance term, and then a potential term. Okay, and yeah, du is given like this, igpu. So this is similar to what we have in the Lagrangian of electromagnetic theory, interacting with scalar field. So, but it's a toy model, so it can be anything in principle. And this is the gauge invariant of d mu phi. Okay. Now, we see there is no mass whatsoever, no mass for b mu in this Lagrangian, right? But and we add, and like I mentioned, if we add the mass term, we get into trouble. Okay, so then what can we do? So what we do is we do a reparameterization of the field, the scalar field. So we write it, so it's we know it's a complex number, so we can write it as a, you know uh, we can write it like this, right? So a phase term e to the power I theta. Theta will be a function of space time, and then uh, some xi of x. Okay, and we can write the xi explicitly like this. So any complex number can be written like this. So some v constant, so it's the small v, not to confuse with the potential, plus some h is a function of x uh, under root 2. So I mean, we can assume that this xi can be written as a sum of constant and a function of x. Okay, and then so this is the reparameterization, and then with this we demand this gauge transformation for the phi. Okay, and for B, we have already this gauge transformation for B. Okay, now if we put these things inside our uh, Lagrangian for a scalar, uh, so you will get, so I'm writing this thing explicitly, and this is the prime, so everything should be prime. Okay, and when you put everything, so b prime mu you put from here, phi prime you put from here, everything if you put, you will, and do some algebra, you will find that you will get an expression like this. So this has been done in the lectures, but I'm just recapping it, and then we will see what does it mean. Uh, okay, so we get these terms. Sorry. And you see that we have terms like this, and this is clearly what we wanted. We wanted a mass term, and so if we write this, sorry, there will be no uh, there should be no prime. Okay, this is without prime, so we wanted this, so we see that we have a mass term with mass given by uh, mass square given by this value. Okay, and this is what we wanted, so we didn't added explicitly any thing into the Lagrangian. We just reparameterized the fields, and we saw there emerges a mass term like this. Okay, now this potential here, uh, this potential we can write it for these parameterized fields like this. So this is the V, and so every field has a minimum energy value, or minimum energy configuration, which is called vacuum. Okay, and to find that minimum energy, you can just we can just differentiate it with respect to phi, and you will see that we get this, and we put it to 0 for the maxima, and we get this condition for the minimum energy configuration. So, and this is what, so this we can write it as, this is just the expectation value of the field, okay, is the mod of phi, which is also, I mean, expect which we call the expectation value of field for minimum energy configuration. Now, so so this is the value of the expectation value of phi corresponding to a vacuum. Now, in vacuum, particle cannot be created with energy greater than minimum energy. I mean, if you supply a minimum energy, you can have particles in the vacuum, okay. And we see that uh, we cannot put the phi to 0 if you want to have a mass term like this inside the Lagrangian, okay. So if you plot the potential, so you get something like this. It's called the Mexican hat potential, and this is the real part. If this is the real part of phi, and then you have the imaginary part, okay. And here these are the minimum values, v by root 2, okay. And you see that you get a degenerate, you can basically rotate around, and you get a degenerate vacuum state. What does it mean is, so you have to choose one vacuum over the another, okay. So this is and when you choose one vacuum over another, you break the symmetry, right. This is what is called the spontaneous symmetry breaking here. So basically, uh, if you want to understand in simpler terms, so every quantum field has a vacuum or the minimum energy configuration, and the vacuum will be degenerate when you get two values of the minimum energy. So if you have E1 and E2, so for example, we have here infinite values of uh, minimum energy of the vacuum of the field. So the physical system has to choose one over the another, right. And this breaks the symmetry that you have. And this is what is called spontaneous symmetry breaking. So suppose there is a vacuum state. It it will not it will be equal to a zero particle state, okay. Plus something which is the vacuum expectation value. Let's call it VEV, that we have calculated. So even in the vacuum, you have some energy. The vacuum is not equal to a zero particle state. Okay, so even in the vacuum you have some particles, and so I mean that this is what it means that the Higgs I mean, so this is uh, this field, this kind of field is called Higgs field, and we see and we say that Higgs field is never zero. I mean, even in the vacuum you have some spontaneous creation of particles, and and so and so if you have any scalar field, uh, it will interact with those particles, and it generate I mean, so it basically based on the scalar field, scalar particles, and it become massive. So I mean, so suppose then you have two interacting fields, psi x plus phi x, right? And suppose phi x does the spontaneous symmetry breaking, and there is no spontaneous symmetry breaking from psi x. So uh, expectation, I mean vacuum expectation value is non-zero for phi, and it is full of, you know, particles, and this will interact, and if it and if the psi interact with this field, uh, it weighs down, so it creates some hindrance, and which would have been, you know, massless. If psi would have been, I mean, zero, where have been zero. So I mean, so to get an analogy, suppose you have a ball, and in a tank full of water. Okay, if you drop a ball, if there is water, it will, you know, uh, it will go slowly inside the water. So Higgs field is like this water, and if you have any particle which interact with the Higgs field, it will gain some mass, so it will move slowly inside the Higgs field. So this is what I mean, kind of a naive picture about the spontaneous symmetry breaking. So this is what I wanted to briefly discuss today in our extra session. Okay, so yeah, I guess this is it. So thank you all, and see you. Bye.